Hi, how are you? This is the continuation of the Chem 1A prep. So today we're doing significant figures. So make sure you have your handout. It has a lot more details in there and examples. Please realize I can only do so many stories and stuff here because we want to keep the videos as short as possible because it's easier to manipulate them and I don't bore you for as long, okay? So significant figures was covered in your high school chemistry. Whether your lecturer in Chem 1A will cover it or not, it depends. In the case of when I teach the lecture, I don't cover it. I just immediately start doing a problem and I remind you of the rules as I do a problem. I just don't do one day of significant figures. I start doing other work and bring up significant figures, okay? We might summarize it as sig figs or abbreviate it as sig figs or SF. So if you have a problem and you have the significant figures incorrect, then you might see, minus 1 point SF, and that's letting you know that you did the significant figures wrong. So when you're measuring anything, and that's what chemistry is about, you're measuring and making compounds and deciding, percent yields and how much did you make and the density of something and the number of moles of something. So all these things require measurements. And so the measurements are only as good as the instrument measuring them. And so you end up then having to worry about how good is that instrument. As an example here of something you've done often in your life, I've blown up a ruler, okay? So we're trying to measure this blue device that ends up here. Now, rulers are in eighths often, sometimes 16ths, but definitely not in decimals, they're in fractions. So I set this one up for eighths, and again, this is much bigger than it is, so it's harder to tell these separations, but halfway through you have 1.5 inches, or 1.5, or 4/8, and then this marker here is for 5/8, and that's roughly 1.62 inches. And you notice that the item is more than 1.5, but less than 1.62. So we know that number is in between there. And now the question becomes, guessing what it is in between those two. And so you are sort of eyeballing this and making the best measurement you can. And so you might measure 1.56 inches, but you realize that that last digit is somewhat uncertain. This value has 3 significant figures. I would say for my measurement, when I'm looking at a ruler, I'm probably good to 0.02 inches. But again, it's your decision to see how good you feel you are at eyeballing that number. But we tend to assume that the error is maybe 1 or 2 in the last digit. If you want it to be more, then you might have to specify it, okay? Now, this whole thing about significant figures also shows up a lot in engineering and machining, but they might call it tolerances. So say, for example, you have a piston in an engine, right? So the piston, you add chemicals here, so you add your gasoline and oxygen from the air. There's a spark from the spark plug, which causes a combustion generating gases that pushes the piston up. You have to design and measure these pistons out very carefully, right? So if you make them too small, then there's a lot of extra space on the side, the gas goes that way, it doesn't move the piston up, and so you get an inefficient conversion of chemical work to mechanical work, all right? So you're not combusting efficiently. If you make it too tight, then there's too much friction, and so the piston has a hard time moving up, and so the same thing again, you're not doing this efficiently. So there's a certain tolerance as to how you design that, or how you measure out that piston. You might have to measure it, to hundreds of a millimeter to make sure it fits the hole that you've created for the piston, okay, the casing for the piston. And so again, tolerances, significant figures, these are all concepts used in science and engineering a lot. It gets even more interesting. So let's go over here and see, for example, some equipment in lab. And clearly these are very crappy drawings, but you should know equipment from lab because you're expected to have had high school chemistry. So you have a beaker. Beaker is just like a really wide mouth container, glass container. You have a graduated cylinder, a much narrower glass container. The markings here might be 10 and 20, but because the cylinder is narrower, small changes in volume represent large changes in the height. And so you might be able to have 10, 11, 12, 13, 14 markings on that graduated cylinder, right? So if you want to measure, say, 12 ml, you most definitely want a graduated cylinder, because whatever you get here is not going to be as accurate as using a graduated cylinder, all right? But clearly, this device has more markings, and so it's going to cost you more, all right? And in lab, we have burettes, and we have volumetric flasks and pipettes that cost more than a graduated cylinder because their necks are narrower. And small changes in height represent, large differences in height represent small volumes, and so you can measure the volume better, all right? And so those devices will cost more than a graduated cylinder. In lab, we have balances that are top loading, and we have analytical balances. The top loading balances are on a counter, and you just put the stuff on there, and there's air, and there's stuff, and it doesn't matter because it only measures to 1/100th of a gram. The analytical balances has little doors. You touch the table, and it vibrates, and it changes the number. We have them in a separate room so that the air and the motion is more controlled. Those measure to the 10,000ths of a gram. Your top loading only costs $200. Your analytical balance costs $3,000. So it becomes, the more significant digits you want, the more the instrument will cost, all right? And then this leads to the situation which a lot of young scientists find themselves out of when they leave college. You're going to work at a company, you're the scientist at the company, and they ask you to buy the equipment. And they tell you, now go buy balancers. And you have to know what you're doing here. You have to understand what the business is and significant figures. You have to be able to decide, hey, the company is going to mass produce, hundreds of grams at a time of salt, let's say. So if it's mass producing, it's seldom going to be weighing to 4 decimal places. So maybe you just need top loading balances and you pay $200 for them, right? And you don't buy an analytical balance and your boss doesn't go, why are you measuring things to 10,000ths of a gram when we're starting with, 500 grams of this? Whether we have 500 grams or 499 grams, it's good enough, right? Or the opposite, you could work at a facility that is going to be measuring, traces of chemicals in water. You go buy a top loading balance, but you were supposed to buy an analytical balance because you were going to be measuring significantly small amounts of metals in water. And so you have to be aware of what is needed so you can judiciously purchase the right piece of equipment, okay? All right, so again, the example here, you have an item that weighs, a little more than 1 gram. You put it on the top loading balance, it says 1.43 grams. So that is good to 3 significant figures, and it's probably up 1 or below 1 from that. That's the error in this, plus minus 0.01. When you go put it in the analytical balance, you get more digits. You get, oh wait, it's actually 1.4327. And so now you've changed that into a 5 significant digit number, okay? Because you used a better piece of equipment. Okay, so let's start some data here. I've given it units because typically our numbers have some sort of unit, okay? So if we look at this, it has 1, 2, 3, 4 significant figures, 4 SF, all right? It's fairly easy when all the numbers are something other than 0, it's easy to figure out how many sig figs. A given number, I gave you 1.243 grams in an exam, then you go, hey, it has 4 sig figs. All right, zeros in between numbers count, right? So it has 1, 2, 3, 4, 5. 5 SF. And this has 1, 2, 3, 4. 4 SF. All right, so that's fairly straightforward. Now I've got to move the camera, so give me a second. Actually, I'm not moving a camera, I'm moving my iPad. Okay. You also hear me walking. All right. So now I give you a number of 25300 grams, so 25,300 grams. Now, when I have a number, a whole number with zeros at the end, one or more, I got a problem because I don't know how good the instrument is. It could be that I had a great instrument that measures to 1 gram, and so this guy just turns out that the last 2 digits were 0 to within 1 gram, or it could be that I have an instrument that only measures to the 100 grams. And then I'm stuck in that those zeros are, I can't tell the difference if it's 317 or 394, right? It just measures to the hundreds, okay? So in this scenario, I have to assume the worst case. If you don't give me information, I am going to assume this only has 3 sig figs. It has to be the worst case. If you want me to better show the possibilities here, then you use scientific notation. And so if I said it was 2.53 times 10 to the 1, 2, 3, 4, right, grams, then I know he has 3 sig figs. If you had said 2.530 times 10 to the 4 grams, then he has 4 sig figs. 2.5300 times 10 to the 5 grams, oops, sorry, still 10 to the 4, then he has 5 sig figs. So we like scientific notation because it's better at representing sig figs. All right, we have another number here, and so it has the 0 in the middle, and it has a 0 at the end, and it has zeros at the beginning, and that's when it starts getting a little confusing, all right? Zeros at the end after the period count, because it's telling me it's good to that decimal place, okay? Zeros at the beginning are telling me the power of 10. So they don't count, they're what's reflected here. Zeros in the middle always count. So when stuck with this situation, if you are confused, write it in scientific notation. So 4.20350 times 10 to the -1, -2, -3 moles. Okay, and then I look at this and I go 1, 2, 3, 4, 5, 6, 6 SF. Okay? All right, now, unfortunately, we just don't get numbers and just report that number that we measured. We often have to do calculations, right? If you're measuring a density, there isn't a density machine. We measure mass, we measure volume, and have to do a division. If you're measuring grams, we transact in moles in chemistry when measuring grams of a chemical undergoing chemical reactions. There isn't a mole meter, so we have to convert it to moles. So there's going to be multiplications, divisions, additions, subtractions, as well as other mathematical operations. We're only going to cover these 2 mathematical operations. There will be logs. The logs will show up in Chem 1B, and then we'll walk you through the sig figs there, all right? So, multiplying and dividing. The answer will have the number of significant figures of the value with the least. So if your operations just has multiplication and division, you go in there and you go 1, 2, 3, 4. He's got 4 SF. 1, 2, 3, 4, 5. He has 5 SF. 1, 2, 3. He has 3 SF. Whoever has the least, your answer gets reported to 3 SF. Your calculator is going to give you 20 SF, whatever number SF it wants to give you, or it's going to give, I should say SF, it's going to give you 8 digits, because it doesn't know how to do this. You are the one who's going to have to write down the number to the correct number of significant digits. Adding and subtracting. This is more difficult by a little bit, and this is where we catch students the most, or students tend to make the mistakes the most. It's not based on significant figures, it's based on decimal places. So we want you to tell us how many significant figures the final answer to these problems have, but the rule that applies has to do with decimal places. And so for me, I can look at the numbers and figure it out quickly because I've been doing this for a long time. But for new people to this, it is often best to set up the operation as a stack, all right? As you would have done it if you were in first grade sort of thing, right? And so this guy's good to the third decimal place, this guy's good to the first decimal place. So what I would do is throw a line, and I know my answers only go to one decimal place. So then I do the math, 3, 4, because my calculator is going to do it, 6, 9, 2, decimal there. And so then I can write here that he is good to 3 SF, right? And that makes it so I don't make a mistake because I have an input with 4 and with 3, and applying that rule might have worked here, but it doesn't always work. Actually, it seldom works. This is an example of that, okay? So this guy's good to the third decimal place, so I'm going to be only good to the third decimal place. So I throw a line there, and it's a subtraction. So technically I have a 0 here, so 9, that turned into a 1, so 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0, so that becomes 10 minus 5 is 5, and this became a 9, so that's what I get, all right? So if I write this, I'm going to round it up, so 5.001 is my final answer, so he has 4 SF, right? And so I started with 2 numbers with 6 significant figures, but because of the nature of the operation and the fact that I'm doing an operation that tracks decimal places, my final answer only has 4 sig figs, all right? And as I state, this is often where students get a little bit, have a harder time keeping track of sig figs. Switching the camera again. Okay. All right, finally we have exact numbers. There are some numbers that are exact, so they have as many sig figs as you want, all right? So if I count 10 human beings in a room, there are 10.0000 and as many, because I can't have a fraction of a human being, all right? 100% of a sample. So if I tell you here's all the sample, then you have 100.0000, as many digits as you want, percent of the sample, okay? Number of atoms in a compound. So we say there are 2 hydrogen atoms for every water molecule. You can't have a fraction. And so if you have to do some calculation that requires that, you have 2.00000, as many as you want decimal places for that calculation. So that's not what's going to limit your calculation. And again, when we start doing calculations with stoichiometry, we'll remind you of this. Conversions within the same unit system have infinite number of sig figs. So there's 100, and you decide 0.0000, as many as you want, ml in a liter. Because that's the definition of a milliliter, okay? So it's defined within that system to be exactly 100 ml. The same thing, a foot has 12 inches. So it's 12.00, as many digits as you want, inches, because it's defined that way. However, if someone then asks you, how many centimeters in an inch? That's a conversion factor between 2 unit systems, and as such, that's going to have a set number of significant figures, all right? So they're 2.54 centimeters in an inch, so that has 3 sig figs. You could get that number to more digits if needed. All right. Okay, and I think the list might include 1 or 2 more things, but you have the list in the handout. So let's practice a little bit here. So for each one, let's figure out how many sig figs. So the zeros in the center count. The zeros at the end count if they're after the decimal place. So this has 5 SF, right? 250 grams, Zeros for whole numbers, if they're at the end, I have to assume the worst case scenario. I have to assume the instrument is only good to the tens because you did not give it to me in scientific notation. So this is good to 2SF. This one, zeros are for position, so they don't count, but that is a 0 at the end after the decimal point. So this has 3SF. Okay? This is all dividing and multiplying. So I count the number of significant figures for each one, and I pick the guy with the least. So I have 4 here, and 6 here, and 5 here. So the answer gets 4SF. Okay? This one is adding, so it's about decimal places. So rather than make a mistake, I set it up. 4.531. So I'm good to the hundreds. I do my math. It's an add. So I have a 1, a 6, a 7, a 3, and then a 10. So notice I have 5. Oops, that's not a 5. 5 SF. Okay? So notice I started with 4 and 4, but my answer gets 5 because when adding and subtracting, it's about the number of decimal places. Here I am doing 2 operations. So based on the parentheses, I've got to do this operation first here. So I go 1.432 minus 0.11. Okay? So this number is going to be there because it's decimal places. I get a 2 and a 3 and a 1. So he has 3SF. He has 4SF. Now it's multiplication. So this guy gets 3SF. All right? Okay, we practice a little. You have a worksheet that you can do in the module with a solution so that you can practice some more. All right, thank you. Next time we do units and dimensional analysis and graphing.